And so, hello everyone, welcome back after holidays. So we have the fourth iteration of this interesting course given by Professor Herbert Huppert. And now he's going to tell us about how to forecast the weather with the principles of fluid dynamics. So Herbert, as always, thank you very much for enlightening us with your knowledge on these topics. And if you could please start.
Well, thank you very much, Sergio, and thank you all for joining. I hope each of you had a good week's holiday and enjoyed the time and are now coming back to work. Well, chapter 4 has really two different sections. One is the development of weather forecasting, and I'll talk about the contributions made by Maury, Fitzroy, Richardson, and others. But this is quite some time ago. Maury and Fitzroy were in the 19th century and Richardson in the 20th century. And then the next part of chapter 4 will be right up to date and talk about climate change and how that's affecting us. We're really very much under stress because of the gradual heating of the atmosphere. Whoops, okay. Well, although mankind had been on Earth for thousands of years, we really knew nothing about forecasting the weather, about what it was likely to be the next day. And there were some terrible situations. For example, this in 1703 was the great storm that came over southern England and moved towards the east at about 100 miles an hour, really quite rapid. In those days, there were no mobile phones or telegraphic possibilities, and 100 miles an hour or so was rather faster than a horse could travel, so there was no communication possible. And this storm just caused enormous problems, sunk many ships, killed 1,000 people. Sorry? Okay, so sorry, was somebody saying something?
I think someone left the mic on mute by accident. So let me just remind people that if they have a question, probably it's better that you write it in the chat, and then I will bring Herbert's attention to it so we don't interrupt the flow. Okay?
Well, I'm quite happy for Sergio to interrupt me to ask a question from the chat, and if I can make things clearer. So that was quite a problem, caused lots of devastation. And this is my college, King's College in Cambridge, and 3 of these towers that you see on the side of the chapel were blown down. We know that, and it must have caused lots of difficulties in Cambridge. Then there was a big problem. The Royal Charter, a ship was coming back from Australia, actually, and it was just off the Wales coast when there was a sudden storm that was very tightly compressed, sunk the boat, caused many people to lose their lives. Some people, as you see in the left, managed to somehow scramble to shore. And afterwards, what was found to be quite either disastrous or off-putting is that just 20 miles away or so, there was another big ship, and it didn't get into the storm at all. It was 20 miles offshore, and the storm was so isolated. Well, the 3 people who, in my opinion, made the greatest developments were Matthew Maury, an American who really started, and Robert Fitzroy and Lewis Fry Richardson. And I'll tell you a little bit about their contributions and about them. The first, Matthew Maury, who was called the pathfinder of the seas, and lived, as you see here, from 1806 to 1873. He joined the American Navy, and he was in the first American naval ship to sail around the world, totally around the world, the USS Vincentius. He was a very serious sailor. He noted the sea and the relationship between the sea state and the weather, and was really very interested in this. Then one day he was traveling in a coach, horse-driven coach as of the time, and it stopped to pick up a lady. There wasn't really enough room in the coach, and so Maori, being a gentleman, said, "Look, I'll ride up with the driver and you can ride in the coach itself." So he rode up with the driver, but it was actually a mistake in some sense, because the driver was very incompetent, was known to be incompetent, and he managed to overturn the coach and the horses, and Maori broke his femur. Now, in those days, that was really quite a terrible thing. He was quite young, but he couldn't really walk properly or maneuver. And the Navy didn't know what to do with him. And on the one hand, he'd been very gentlemanly, and he'd caused this problem to himself by allowing a woman to take his place. On the other hand, he couldn't really work on ships anymore. And so the Navy had an idea and said, you know, since the beginning of the American Navy, we've asked captains to submit descriptions of what they've seen as far as the weather and the sea state is concerned. And they're kept in a big building in Washington, but nobody's ever looked at them. So why don't you look at them and see what you can find out? And so he was the first person to really look at sea states and weather possibilities. And after a terrible disaster where the 1954, where some 50 miles off Newfoundland, two ships collided in the dark, Maori had the great idea of having definite lines along which ships should sail. There'd been differences for years, decades in driving on the left or driving on the right. And he invented the idea of ship lanes so that ships couldn't smash into each other. And that was really very important. And by looking up the sea states and knowing what the wind conditions were, he sometimes saved as much as 3 weeks off the time of a crossing. Really very capable indeed. But then, unfortunately, the Civil War erupted, and Maori was a Southerner, and he understood also how to make detonated sea mines, and he downed more Union ships than all other methods combined. And in various places in the north of the United States, he's not at all liked. Though in the Maine Oceanographic Institute in America, there's a Maori Lane after him. But some people are really very annoyed. And he then wrote a book, The Physical Geography of the Sea, and is called here in this biography, the father of oceanography. He then moved to France because he was not liked by the New America because of his southern aspects. So this is Maori sometime later. Now, the next one I'd like to tell you is Robert Fitzroy. He was the second governor of New Zealand, and he was the first director of the Met Office, the Meteorological Office, a really very fine man. And I always find it surprising. He was related to Charles II, the English king, the founder of the Royal Society, and his mistress, Barbara Villiers, the Countess of Castlemaine. And she had 5 children with him, and one of them fathered Robert Fitzroy. It was said she was tall, voluptuous, and a highly sensitive, sensuous mouth. Quite a business. He went south, and his captain committed suicide, and at a very early age, something like 21 or 22, Fitzroy rather was put in charge of his ship. Let me get there right. He then took the Beagle with Darwin, the famous Darwin, down along South America and around the world. And he and Darwin had great arguments because Darwin had dreamed up this new idea of natural selection. And Fitzroy was very, very religious and didn't like hearing that at all. He was a wonderful sailor and commander, and you can partly see that in one of his entries is that, because he was a very good keeper of records, that there were 3 really large rogue waves, as he called them, and he had great difficulty keeping the ship afloat. And he wrote in his diary, if a 4th one had come along, I think I just wouldn't have known how to handle it, and the ship would have gone under. On the other hand, one of his underlings wrote in his diary, any other captain would have downed the ship on the 1st wave. Only Fitzroy was able to take 3 waves in a row. He was really remarkable. He invented a barometer, the Fitzroy barometer, because he realized that there was a relationship between the atmospheric pressure and the sea state. And so that was an important fact. And also noting that there was a difference between a rising and a falling pressure, which made differences. He was made the Director General of the Met Office, and he issued the first newspaper weather forecast in 1861, rather slight, but still very useful. In the north, there'd be moderate westerly winds. To the west, there'd be moderate southwesterly, and in the south, there would be fresh westerlies. Not very detailed by today's standards. Here are some of the later reports. He would get reports from a number of places around Britain, and he would then see that they were published. The Met Office had in those days 15 telegraphic stations, which sent observations to London at 8 a.m. to make these forecasts. And forecast is a term that Fitzroy invented. And as I said, with the first printed weather forecast appearing in 1861, 160 years ago or something like that. And it was not too bad. Now, of course, communication got more rapid with time. Samuel Morse's first telegraph line ran between Washington and Baltimore to inform people of what the weather was like. So they didn't have these large storms, came totally unprepared for. And there were some 2,000 miles of telegraph lines in the US by almost 1850. The first line in Australia was overland, linked Australia to the rest of the world. And the important part was by the engineer Alex Dodd, whose wife was called Alice. And that's how the name of Alice Springs in the center of Australia originated. Anyhow, Fitzroy's Met Office had some 15 telegraphic stations, and they sent observations every morning. Now, instead of 15, we have something like 4,500 surface stations reporting worldwide. But of course, we also have many satellites. And here's the memory of him, Robert Fitzroy, the pioneer of weather forecasting, and who took Darwin to the Galapagos. The next man I'd just like to tell you about is Lewis Fry Richardson. He was nicknamed Prof, and his biographer said on the front page, was Prof for prophet or professor? Very interesting man who was an undergraduate at King's College. Again, my college. This is now the sun shining down on King's, the front of King's. And after he'd finished his undergraduate degree, he went and got a job in a peat mining business up in the north of England. And what was very important in the peat mining was to know how quickly water seeped through the peat and what the form was like. So he knew of Darcy's equation, which we've talked about, the flow through porous media, and he tried, of course, by hand to get solutions under various different situations. And he found that he needed quite a large grid scale in order to finish off the calculations in a reasonable time. And he knew that there were errors in having such a large grid scale. And so he invented what we now call Richardson's extrapolation to the limit, basically saying, let's take a certain distance and then take half the distance and then half that distance and see how the error changes and see if we can evaluate what the functional form of the change is. And he did that very successfully and worked that out. Then came the war, World War I, and Richardson was a Quaker, and he definitely wouldn't fight in the war, but he did go on the ambulance unit and came very close to the front line. And he took with him the details of the weather one Sunday morning at 6. And he spent something like 4 or 5 months by hand working through solving the Navier-Stokes equations, working through what the weather should be like, solving the equations, which I'll tell you in a moment, what the weather should be like in 12 o'clock at noon. And he got it hopelessly wrong. And he knew he'd got it hopelessly wrong. He was very disappointed. And the reason was he had to take a very large grid. It was 200 kilometers in the horizontal in both directions. And there were sort of 5 grids in the, or 5 boxes in the vertical direction. So about 2 kilometers there. And he time stepped by 3/4 of an hour. Now, we learned much, much later that such a system is unstable. And the time step was far larger. But of course, he had to do this by hand, not in the days of, or the days of computing today. He then had the idea of having human computers, and he would have a number of humans, 64,000 he calculated, in a big hall, and each set of human computers would represent one country, and they'd work out what the weather was like in Australia, and then they'd pass it on to the United States because it had gone across the Pacific and there were connections between all the various countries. And he imagined that he would sit there as a conductor and have each one of them make the calculation in the time that's needed. He calculated that he needed something like 64,000 computers, human computers, to do that. And it turns out he made a mistake there, unfortunately. there's something like 256 needed to really be able to do the calculations. Now, 256,000 humans doing the calculations. Now we have calculations done in petaflops. That's 1 billion calculations each second. So you can see 64,000 is far too small. 256,000 is even too small. Unbelievable today what we do. He wrote a very important book, Weather Prediction by Numerical Processes. His numerical skills got to be better with time, but still a lot more to be done. And he is often cited for this little poem, the only first 4 lines of which are really remembered. Big worlds have little worlds which feed on their velocity, and little worlds have lesser worlds, and so on to viscosity. And this is really a description of turbulent flows. Big worlds are the big turbulent eddies, and they transmit part of their energy to the smaller worlds, and those transmit them to the even smaller worlds until the Reynolds number becomes sufficiently small, the scale is sufficiently small that viscous effects become important and dissipate. And you have to be able to calculate all of that in the problem. He also became very disillusioned after the war and with weather forecasting, and he wondered why it was that there were wars. Why had there been so many wars? And one of the things that disturbed him greatly is his peace-loving country, Great Britain, had been in more wars than any other country, and that he couldn't understand. And so he somehow thought, and for reasons that he didn't write down, so I don't know why, that maybe the propensity of going to war would depend on the perimeter of the country, not on the number of people in the country or not on the area, but somehow the perimeter. Well, if the country is rectangular, then to work out the perimeter is very easy. But if the country is complicated, like Great Britain is, and most countries are because they have shorelines, it's not so easy. So what Richardson did is he got a big map of Great Britain, and he put it down on the table, and he took some dividers and separated them by 250 kilometers as far as the map reading was concerned, and worked his way around the coastline of Great Britain and gotten a certain length. And then he thought, because he'd understood about extrapolation to the limit, maybe he should make them slightly smaller. So he made smaller opening, 25 kilometers, went around the coastline again with this smaller opening, and found, of course, it was very much longer. And that was really the beginning of so-called fractals, that the length of a jagged perimeter depends on the measuring length. He put forward some of these ideas in this book. This is now a photograph that I like. This is taken at Euston Railway Station in London, and of Matthew Flinders, who sailed around Australia, who was the first person to sail around Australia, and he was famous for having sailed along with a cat. And he then came back to England, was buried near Euston Station, and when they started to build the station, they found his coffin. And so they decided to make a statue of him. And you see him here with dividers, just like Richardson, measuring the length of the Australian coastline. So I always say, Matthew Flinders developed fractals long before Richardson did, though of course it's not known what he did with the results. Richardson then worked with the very famous oceanographer Hank Stommel, and the two of them were interested in the turbulent motions in Loch Long, a large lake in Scotland, and to the amusement of people around, they threw parsnips into the sea and measured how far apart they were and how they moved with time, and they wrote a nice paper together. Now, it's got to be a continuation of F equals ma, like the great Newton, who's on the top left hand, said, and that brings us down to the Navier-Stokes equations. I show you the Navier and Stokes photographs here, which we've mentioned before. The inertial terms on the left-hand side and this all complicated u dot grad u term, and the pressure gradient driving the flow, the viscous dissipation term, the del squared u, and then other forces that might be there. Now, there's something called Bayes-Ballot law, very important and definitely correct. And in the Northern Hemisphere, it says, if your left hand is on the lower isobar and your right hand on the higher isobar, in other words, there's a pressure that's increasing to the right, then the wind will be on your back, come from your back. Now, how does that make sense? How can it be that the pressure goes from one hand to the other and the wind is at right angles? Well, the important thing here is there's a Coriolis force, which I haven't mentioned yet, and that's due to the fact that the Earth is rotating. And there's a term that has to be added in there, which is 2 omega cross u, which is due to the fact, which I've never understood, I must say, that Newton understood that F equals ma was with respect to the fixed system of the stars, and that if you were rotating, he knew that that would make a difference. He didn't work on it much, but he knew about it. And the weather, you have to solve this equation with all its complications, and of course include the Coriolis force, which means that the balance of forces leads to a displacement at right angles to the pressure gradient. The important parameter is the so-called Rossby number, which is some typical velocity over the Earth's rotation and the typical length scale. And when the Rossby number is small, then rotation is important. If the Rossby number is large, it could happen if the length scale is sufficiently small, or if the velocity is really large, you can't change the rotation of the Earth, then the Rossby number is large and rotation doesn't play a role, but it does play a role. Then I'll just mention in this little historical sketch that Francis Beaufort was an Irish scientist who also looked into weather, and some people think he made a big difference. So what I'd like to take home messages from here is that for thousands of years, humans had no idea how to predict the weather or associated state of the seas. While records have been collected for ages, Maury was the first to analyze them, starting in 1839, because he broke his femur and the Navy didn't know what to do with him. Fitzroy developed a really better understanding of the sea and the weather, and was the founder of the British Meteorological Office in 1854, and still, I think, one of the, or the best in the world. And Lewis Fry Richardson developed numerical methods to the weather, and then did other things on psychology of war and looking into war and initiating fractals. Now, I'm afraid, and I should have said this at the beginning, I don't know if there was a Chinese contribution to all of this. It's not talked about. There may be some famous Chinese weather forecasters, but I'm afraid I don't know about them. Well, now I want to go on to be a little bit more mathematical. So far, I've really just been historical and said, part of the problem is that there's a huge amount of different things that go on, which you have to understand. Their radiation and wind waves and convection in clouds and surface shapes and everything. And so what you need to use are the physical laws of the atmosphere, which are the gas laws, because the atmosphere is mainly gas. So we do need to take into account the water vapor that's in the clouds, and that's Boyle's law and Charles's law. So we get some relationship between the pressure, the temperature, and the density. Then we have the conservation of mass. Air can neither be created nor destroyed. So that's the continuity equation. The conservation of water, liquid and solid, and you can have gaseous water too, of course, and rain, so it's in the liquid state, and ice. Then the Navier-Stokes equations, putting in how the velocity changes with the pressure gradient, the Coriolis force, and friction. And then the thermodynamic equations telling you what the relationship is between the temperature and the pressure. So this gives you 7 equations, and you're going to need 7 unknowns, and those, 7 variables or unknowns to go with that. And here are basically the equations, the 7 equations. The first is saying what the effect of the horizontal pressure gradient is, dp dx. Second, the horizontal pressure gradients in the other direction. The gas laws, P is the rho RT, hydrostatic equation, the temperature, which is going to be changing, partly due to being driven along and partly due to anything that makes temperature in the atmosphere, the continuity equation, and then the differences between sources and sinks, as you saw on the slide 2 or 3 ago. You can have rain, you can have water coming up from the surface. Really quite a complicated business. So this is hopefully a summary of what we can do. The atmosphere is a physical system. Its behavior is governed by the laws of physics. So in that sense, it's interesting it took so long before we got further with it. The laws can be expressed in terms of mathematical equations. Using observations, we can get today's weather, and then using equations, we can calculate, hopefully, tomorrow's weather. Equations are very complicated, clearly nonlinear, and powerful computing is needed to do the calculations. And I'll tell you a little bit now about the history of those computing. The project was really first set up to do some computing by Johnny von Neumann, excuse me, just after the end of World War II. And he proposed money to develop some computing facilities towards getting somewhere with weather prediction. And he realized he needed some really good observations and then how that would work. This is now, and I show this for people who are not used to computers, this is a very early computer, the ENIAC it was called, with lots of tubing and elements, and it was sort of slow compared to what we do today. But the people who worked on it were von Neumann, as I've already said, Jules Charney, who was working with von Neumann in Princeton, and Fjordhoff, who was also there. And they wrote the first paper on the numerical integration of the barotropic vorticity equation. So solving the equations. The ENIAC was the first computer, as I've said. It had 18,000 vacuum tubes, 70,000 resistors, 10,000 capacitors, 6,000 switches. Can you imagine that in today's parlance? Incredible. And it took up 140 kilowatts. Now, a tricky question. If astronomers can make accurate 76-year forecasts, we know exactly when planets are going to rise and when we're going to have a solar eclipse or something like that. Why can't meteorologists do the same? Both of them basically follow Newton's laws. The problem is that astronomers can do it because it's all very straightforward and not turbulent, not out of control, if you like. And meteorologists can't do this. And an indication of the difficulty was shown by Ed Lorenz when, in a paper written in 1963, he showed that this simple system, this was the simplest system he could work out, 3 first-order differential equations, x dot in terms of x and y dot in terms of x and z, and that's where the nonlinear part comes in, the xz, and z dot in terms of xy, that the solutions were very sensitive to the initial conditions. And he apparently got onto this idea because he was sitting next to a man at dinner once, a scientist, and he asked the scientist what he was doing. And he said, well, I'm making some really very trivial but long time needed calculations. And I find out sometimes I'm allowed to use the computer over the weekend and I can run them over the whole weekend, but sometimes I can only use the computer for an hour at a time. And strangely, I get different results depending upon whether I integrate for a whole 2 days or just an hour or so. And Lorenz realized that what was happening is that when you take it out every hour or so, then you cut off the accuracy of the final state, which you then put into the initial state. So you slight change the initial conditions and you get different results. And Lorenz realized that and thought of this very simple system. And occasionally it said Lorenz demonstrated with skill the chaos of heat wave and chill. Tornadoes in Texas are formed by the flexes of butterflies' wings in Brazil. And this is really a very important fact, that small changes like the flap of a butterfly's wing can make a difference sometime later, sometime or some distance apart. And this is true, I think, in human life as well, that you just happen to meet somebody or do something and you can be influenced strongly by that. Okay, I just want to say, well, I didn't want that. Oh, no, that's then the end of this section. Whoops, I'm sorry. That's the end of this, and I'll now go on to talk about the climate. So what do? I need, we still have enough time to, I need to get another, are there any questions in the chat, Sergio, while I get to the next one? He can't hear me. Sergio, can you hear me? Are there any questions in the chat that no questions in the chat? No questions. Okay. Right. Then let me see that I can get the next one. My PowerPoint. West. Oh, there's so many that I've looked at last night. Oh, come on. West U3A climate, I think it is. Yeah. So now I want to have a slideshow and play from start. Okay. Well, now I want to talk a little bit about climate. We won't finish this today, but we'll begin. And I'll tell you something about the background science, then talk about the current situation, tell you about some theory and experiments, alternative sources of energy, and end with some take-home messages. And these two slides at the bottom are how we don't want to end up. Either on the left-hand side, you see with rivers overflowing and the ocean height getting larger, which it's definitely doing and causing problems, or to have severe droughts, as you see on the bottom right. That's really the problem. The extremes are developing more than they were in the past and causing us a lot of trouble, bushfires and all. So the work was really
Herbert, can you show the slides?
Sorry?
We can't see the slides.
Oh, have I stopped sharing?
Yes, you forget to share the slide.
Oh, do I have to? Gee, where I can't now see where I share slide. I didn't think I'd stopped sharing. Oh, share screen. There we go. Desktop OneNote. Is that working now?
Yes, okay now.
Okay, well then I'll play from the start. Oh, I'm sorry that you couldn't see that. This was the slide that I wanted to talk about. We're going to talk about climate and the effect of burning and putting carbon dioxide into the atmosphere, which is causing us these problems, flooding, as you see on the left-hand side, and on the right-hand side, total evaporation and trouble. Sorry, so I can now go on? Yeah? Now I can't hear you.
Yes.
Yeah? Okay.
Go on, please.
Then, well, thank you for stopping. That would have been embarrassing if I'd found out I'd gone through the slides without showing you. Excuse me. Well, the first person to really consider the problems that we're faced with now, or realize the problems we're faced with now, is John Tyndall, who was a famous scientist, also an extremely capable mountaineer. And he became director of the Royal Institution and the previous director, I like saying, was a previous PhD student of mine, Sean Fitzgerald. Anyhow, Tyndall just wondered once, I know the input of the sun onto the earth, so maybe I should be able to calculate the average temperature. And he knew what that was too, but he thought it would be fun just to work it out, knowing the solar input onto the earth, the radiation that would come back from the ground. So he thought that would be interesting. And he got that it was minus 15 degrees, the average global surface temperature. Now he knew that wasn't right. And he wondered for a while why it wasn't right. And then because he was a Victorian and he knew about greenhouses or glass houses, he knew that the radiation that comes into through the glass is then changed on reflection to be shorter wave, and the glass can trap that in and warm up the greenhouse. So we thought, that's interesting. Maybe that happens on the earth. Maybe the atmosphere acts like a greenhouse. So he first measured the capturing ability of nitrogen and then of oxygen, the most common elements, and they were minimal. That was no good whatsoever. And he was really very upset about it. And then almost in the last minute, he thought, what about carbon dioxide? I know there's only a little bit of carbon dioxide, but maybe that'll make a difference. So he took into account the amount of carbon dioxide at the time and got something like plus 15 degrees. And that was much better. So he was the first to show that the carbon dioxide in the atmosphere, which, as we all know, is increasing now due to human beings' activity, the carbon dioxide content was really causing a lot of trouble. Now, you can look at that in another way, or justify it if you like. If you look at the temperatures on Venus, they're normally something like 470 degrees centigrade. The temperature on Venus is very much larger than it is on the Earth, and it has roughly the same solar input. Now, how come? Well, the reason is that most of the atmosphere of Venus is made up of carbon dioxide. And so that plays a large role and insulates the planet this way and increases the temperature. Now, it's not right to say that he was the first person. Actually, a woman called Eunice Newton Foote, an American, did the same sort of experiments some 5 years beforehand. And she wanted to talk about them at a scientific meeting, but it was thought to have a woman describe work at a scientific meeting was not quite appropriate. So Professor Henry, a man, was asked to do it. And the thing that I always find interesting is that, as is often the American tradition, a married woman takes as her middle name her maiden name. So when she was born, she was Eunice Newton, and her father was called Isaac. So he was called Isaac Newton, not the famous Isaac Newton, of course, but I always think it's fascinating how his parents decided to call him Isaac. Well, the Earth is a complicated system, and I think, Sergio, it's now sort of 9:50. This is where I should end, isn't it? And talk further on Friday.
Yes, can you hear me?
Okay, and we'll talk about what effect carbon dioxide has and how it influences each of these processes and how we analyze that.
Oh, okay. So does anyone has any questions for Herbert? I think this lecture was very interesting for me because of the history.
Well,
So,
I hope, okay, not many equations, but some.
yeah, but then I was wondering when this well, I don't, you gave us many names, many historical names today, but then you were referring to this first person who detected some chaotic behavior in the differential equations. But
Lorenz.
yeah, Lawrence, those equations were not based on Navier-Stokes, right? Were just a non-linear system of equations.
They were the simplest system which Lorenz thought would show sensitivity to initial conditions. I mean, you've got to remember he had not very good computing facilities by our standards in those days. So he knew it had to be non-linear. We all know that linear systems have unique solutions. But what he wanted to show was that these nonlinear equations, if you add a slight difference, then they can go off to something quite different. And that's important in fluid mechanics because slight differences can really make or slight differences in initial conditions can make for quite considerable differences in final conditions.
But then, well, of course, I'm not an expert in this area, but I know that usually there is a difference between climate and weather. So weather is, of course, random, chaotic, kind of unpredictable. But climate, in long time ranges, long time spans, somehow it can be predictable. It's like this random of chaotic on instabilities, they're filtered out on the time averages, and then that time average behavior is kind of predictable.
Quite right. That's really the difference between the two sections, if you like, of chapter 4. That on the short time scale, it's really difficult to know often what the weather will be like in a few days' time, though we're getting much better at evaluating that, partly because we have much better reporting facilities and satellites giving us good, accurate initial conditions, and partly because we just have better solutions. But then there's the climate, which also has some variations on it. There are hot summers and cool summers, and we don't quite know how to predict those, but we do know that things are getting hotter and hotter because of the carbon dioxide content of the atmosphere.
Yes, of course, that's predictable. That's very predictable. Okay, we have a question. Yeah, we do have a question in the chat box. If you could have a look at it.
How do I get into the chat box? Oh yeah, here. Actually, you can, no, sorry. Forgive my stupid question. I'm sure it's not, even before I read it. If the climate is a chaos system, what is the point of making a relatively long-term or week or so fasting? What if something happened in this period of time and caused instability in some way? Well, that's a very good question. It's not at all stupid. Some week-long forecasts can be reasonably accurate because although the initial conditions aren't that well known, the change has not led to really large changes. Some can be bad because we haven't just had enough data to make a good estimate. Now, what's the point of it? Well, this is, I think the main answer is financial. It makes a huge difference in lots of financial situations, whether you can say that it's going to be rainy or not. And one example that I'll tell you about later on, I think, is included in Southern Ireland. There was to be a big charity event on a Sunday. And a few weeks before the event, one of the people on the committee said, you know, we're really planning and putting a lot of money into having quite a number of people here. What if it's terrible weather and pouring with rain? That would, we should insure ourselves against that. So they looked into it, and the insurance was quite expensive. So somebody else said, I know, why don't we ask the British Met Office to run their weather forecasting schemes? I think this was about 10 days in advance, and see how it goes. So the Met Office came back a few days later and said, look, we have 10 different schemes, and we've run all of them with the observations that we have. And this was now some 20, 25 years ago. And in not one of the 10 different schemes does it rain. So you're perfectly okay. So they didn't take out any insurance, and you can imagine what the end of the story is. With the rain.
Okay.
and
Right.
they a lot of money.
Yeah, I can imagine. Okay, so well, okay. Is there any other question? I think if not, then we can finish here. And then the next lecture is on Friday, where we're going to continue. And now what I can see from the slide, this is a very complex system, no? Involving different kind of Reynolds numbers with groundwater and of course the atmosphere. So that's going to be very interesting.
Okay, well, I hope so. I hope you'll all find it.
Okay, thank you very much, everyone, and see you on Friday.
All the very best, Sergio, and everybody else.
Okay.
There's one new message it says here.
Oh, there is. Oh, okay.
Yeah. Okay. Thank you.
Okay. Bye-bye.
Bye.